Welcome. We're happy to have you here for today's SURF webinar. SURF, or the Sustainable Remediation Forum, is a nonprofit organization, and it's really dedicated to advancing sustainable remediation. And the group is primarily made up of a number of people that represent site owners, regulatory agencies, academia, consultants, specialty vendors, and the public. If you're interested in more information about SURF, please feel free to visit our website or reach out to any members or current board members. You'll find that on the website. And the website has tons of great information, so I'd encourage you to visit. There's a lot of free info, including white papers, case studies, links to some of our previous webinars. Also encourage you, if you haven't already, sign up for our newsletter. You'll get a SURF Break newsletter that highlights kind of what SURF's doing and opportunities to get more involved. So all kinds of great information there. For those of you new to SURF, thank you for attending for today's webinar. We'd love to have you sign up and become a member, but again, feel free to check out the website, see all the information there. And for you SURF members out there, don't forget it is a new year, so go ahead and renew that membership. We wouldn't be able to do these great things without all the support of our members and sponsors, so thank you. So today I'm very pleased to introduce Joe Ricker with EarthCon. He's going to present on how to achieve your sustainable remediation objectives using Ricker Plume Analytics. And I've had the pleasure to work with Joe for the past few years, so I think you're really going to enjoy this presentation. For more than 20 years, he's helped clients optimize their remedial solutions in over 30 states, as well as at sites in both Canada and Brazil. He's a licensed professional engineer in 26 states and has a BS and an MS in civil engineering. So throughout the presentation, you guys will be muted, but feel free to ask questions using the chat function, and we'll have a Q&A at the end. With that, Joe, the presentation is yours.
All right. Thank you, Kyle. Let me get situated here. Okay, so like Kyle said, we're using the term Plume Analytics Tools. So I'm using the buzz term analytics. It's you can see the definition here. I don't want to have to read it to you, but the idea is, taking complex information, distilling it in a way, that makes sense, that we can communicate what's going on to a regulator or to a stakeholder. So that's the idea of analytics. It's just taking all of the information we have on remediation sites and then using those data to tell a story, essentially. And so that's the idea with analytics. Excuse me. So what I want to do here is list just a few of the benefits that I'll walk through all of these, and you'll see how they're played out on just 3 different site examples, but not just enhancing, project management capabilities, but using it in ways to demonstrate natural attenuation. That's a big one. If we want to show that a plume is stable or decreasing, that's a very sustainable remedy, to not be doing active engineered remediation. So a lot of times we have to be able to demonstrate that M&A is occurring, effectively over time. Another benefit you can see is a very strong sustainable benefit as well, and that's termination of systems. I found in our industry, gosh, over 20, 25 years, we're really good in our industry at turning systems on. Sometimes I've found that we're not so great sometimes when it's know what time it is to turn them off. And so these tools really help evaluate termination of remediation systems, getting to that point where you can do natural attenuation going forward. And then another strong area where these tools are beneficial is in optimization of groundwater networks, reducing your network, reducing your analytes, reducing frequency of sampling, just all kinds of great tools. And I'll use examples to show all of these as I go through it. So these are just the 4 primary tools, so to speak, in the toolbox. And the platform, if you will, is what's known as the Ricker method plume stability analysis. And that is a method that I developed years ago. It's published, peer reviewed and all that stuff. And just I've got a link here. You can this is the original article, and this is in the public domain. It's freely available. You guys can access that. But that is the basis for a lot of the tools that I'm going to show stem off of that. And it's really stepping away from a well by well trend analysis to a whole plume analysis. And I'll talk more about that in a minute. Spatial change indicator is another tool we use, looking at spatial changes within a plume through time to evaluate a lot of different ways a plume is behaving. Remediation system benefit analysis. And what that is, it helps answer the question, if you have a decreasing plume in the presence of a remediation system, we always like to ask the question, is the plume decreasing because of or in spite of, my engineered remedy? And so this helps answer that question. If we can, helps lead to maybe a pilot shutdown of the system to evaluate, if it can continue without operation. So just a way to evaluate benefit of a system. And then lastly, well sufficiency analysis, and these are all patented algorithms here. So what that does is helps us optimize the network. Can we reduce a well network? And I'll explain that more here momentarily as well. So what I've got is really just 3 site examples. I tried to get a sampling of different sites, that we might want to look at, and that you guys could, hopefully would apply to something that you may have seen in your practice or in what you're dealing with at your particular sites. So the first one is a former chemical plant. And this site, this site is in Canada. So for the folks in the US, we're typically in acres and pounds, or areas in acres and pounds for the mass. In this case, we're using hectares and kilograms, but no big difference there. So the idea is this site has these disposal lagoons. There's a groundwater plume going off to the northwest. And you can notice here the data is 1984. The plume map you can see here is nothing necessarily new. But what the Ricker method is, it's a way to evaluate plume metrics throughout the plume. So, and those are tabulated here, the areal extent of the plume, the average concentration, which is a spatial integration over the areal extent. And that's all described in the paper. You guys can have that if you want it. And then we do a mass estimate based on the area and concentration. And then you'll notice in the middle here, this yellow cross in the middle, that's the center of mass or centroid of concentrations. So notice the date here is 1984. There are 90 plus sampling events since 1984 before the site got terminated or turned off, or the system got turned off. And so what I'll do is I'll animate this. Now you can see over time, the idea, you can see now empirically how the plume is behaving. And that's the idea of the Ricker method. That's all this is a straight up Ricker method analysis where we're creating isopleph maps for every event through time, and you can see how it's behaving. You can look at the metrics at the bottom, kind of track that as it goes. You can track what the center of mass is doing. Just a really good way to see visually how a plume is behaving. And so this goes all the way through 2018, and that's when we stopped doing analysis because we got a closure here. But really good way to see that. I want to stress that this is not a model. I'm not calibrating, to any boundary conditions, things like that. This is really empirical data analysis is what this is. So once we show the videos, we can then look at the trends in those metrics. So we can look at the trend in the area, average concentration, and mass indicator, and then we can do statistical analysis on those data. So on the right, you can see we're looking at Mankindle and regression, just evaluating what the trend behavior was, over the course of this remediation period. Notice the shutdown here was in 2015. I'll talk more about that in a moment, but we have, roughly 3.5 years of post-shutdown data as well. And we can evaluate those periods statistically. And that's really what we're doing here, coming up with an objective way to evaluate plume stability. Is it truly stable or not? So after we look at that, we can then look at the center of mass. So with the center of mass, we can post all the centers of mass on a single site graphic and look at how they move through time. So if you look at this, all 90 or so centers of mass are posted on a single graphic. The darker colors are the earlier data, the lighter colors are the more recent data. And you can see over time, just visually, you can really get a sense of the migration of the center of mass moving back towards the site. And that's an up gradient shifting in the center of mass. Just again, another way to look at stability of a plume by looking at its center of mass. This is a pretty strong, stable signature in the sense that it's moving up gradient back towards the site. Again, the natural groundwater flow is to the northwest here, and we see a southeast trending center of mass. So again, and you'll see this on other examples as well, but just that's a really good way to evaluate migration and stability as well. And so the next thing we'll do is move into one of those other tools I mentioned, and this is the spatial change indicator. So what we're doing with this is we're evaluating now spatially and temporally. So not just looking at temporal metrics of area, concentration, mass, we're looking at spatial changes over time as well. So again, I put the first plume map on the top left. The very next map in the series, the very next sampling event is in the bottom left. And so what this analysis does is it compares them spatially. So we essentially subtract each sampling event from the original baseline sampling event. And then on the right is a resultant plume, if you will. Anywhere that's blue, concentrations decreased from the base event. Anywhere that's red or pink, concentrations increased from that base event. And the gradational shading gives the general idea or extent of increase or decrease. Now, this is qualitative. This lets you see generally where the plume is getting bigger, generally where it's getting smaller through time. Now on the bottom, we also have quantitative or objective metrics as well. We can look at the amount of change, on a percent basis for area, concentration, and mass. And then we can also look at the magnitude of change. So all of the red represents an increase, and we can quantify that. All of the blue represents a decrease, and we can quantify that as well. One thing I forgot to mention here, there are pumping wells at this site. So there's a pump and treat system at this site from 1984 all the way through shutdown in 2015. So I'll play this here, and it's really neat. You can see the effect of attenuation. What I like to see, what we like to see, is the building of blue, I call it. The more blue you see, the more attenuation is occurring. The very dark blue is 100% attenuation. It no longer exists in those areas. You see the darker blue throughout the core of the plume, just a little bit of red in the upgradient areas, and we're still only in 2010. So we just continue all the data. Really strong way to look at spatial movement, spatial change of within a plume over time. And then we see it all the way at the very end, significant reduction throughout this plume. Just a little bit of pink, which makes sense. This is where it's sourcing. These impoundments have been closed, they're capped, but there's still some back diffusion, there's still a little bit of sourcing, but significant attenuation out here in the plume. Some of that due to pumping. Okay, and we'll talk more about that in a moment as well. So again, just a really strong way of looking at these data. And so what we can do now, we saw all of that attenuation within that plume. So the question is, remember my question, well, was that decrease, was it because of, or was it despite all the pumping, that was going on at the site? So let's look at mass in place reduction relative to mass removed by the system. So that gets into that remediation system benefit analysis tool. So we're going to focus on this part of the data set. So again, from the when this capping event occurred all the way through system shutdown, I'm going to look at this mass in place and compare it to mass removed. So on this top trend that we're looking at, you can see the mass in place trends. So that green trend you're looking at, that was phenol. That was the compound that we were looking at in those plume maps. And you can see the rate of mass reduction from about 97 through 2014 when the system was shut down. And you can see that the plume was decreasing at a rate of approximately 122 kilograms per year. I've also included the two additional compounds, the primary constituents at this site. So they made obviously 2,4-D and 2,4,5-T. These are herbicides used to make Agent Orange. This company made a lot of it into the 60s and 70s, supporting obviously the Vietnam War and all that, making Agent Orange. But anyway, you can see the behavior of these plumes as well. So 2,4-D in the blue, the 2,4-D plume over that period of time decreased at about 100 kilograms per year. The 2,4,5-T plume over that period in the red decreased about 15 kilograms per year. So now on the bottom, what we're going to look at is the mass the mass removed by the system. Now look at this. You can see the system was recovering, the pump and treat system was removing phenol at a rate of about 60 kilograms per year, but the plume was decreasing at 120. Okay, so 2,4-D was being recovered at approximately 16 kilograms per year, but the plume was reducing at 100 kilograms per year. Same thing, 245T, plume was, or the system was removing 3.5 kilograms per year, but the plume was decreasing at about 15. So in all, the plume was decreasing at a greater rate than the rate at which it was pumping. Just kind of tie these all together. You see the system was recovering mass at about 77 kilograms per year, but the plume was reducing at 237 kilograms per year. So what's the reason for that? Why is that happening? Well, doing more investigation, we can look at geochemical data, look at other things, but we found the best way to do that is to, really biodegradation was most likely what was causing this plume to decrease at a greater rate. So what we did is we did a trial shutdown. By showing all this data to a regulator, it really helps them see the data, what's going on, and moving into a pilot shutdown type system, really easy to do. And in doing so, evaluating plume behavior, will it continue to decrease in a shutdown mode or stay stable in a shutdown mode? And that's what we did. So without going into all of the particulars, I'm just going to show you the shutdown data. So here's the phenolics data. I've kind of zoomed in on it. I'm going to focus on the mass trend at the bottom. You see the decreasing trend up until shutdown, and then after shutdown, the mass trend was really stable. It was no longer decreasing, but it was also not increasing. I want to make a point here. Phenol or phenolics, total phenols, is a daughter compound of everything that is degrading at that site. All of these chlorinated herbicides, there's some chlorinated pesticides. They all, a lot of them break down to phenol, pentachlorophenol, chlorophenolic compounds break down to phenol. So the fact that this is a daughter compound that's stable is actually a good thing, to see at the site. Now look at the other compounds, 2,4-D. 2,4-D was decreasing. Here's the shutdown. Look at the post-shutdown data. Statistically, it's still decreasing. And interestingly, that rate of decrease post-shutdown is greater than the rate of decrease pre-shutdown. So shutting the system off actually had not just a neutral benefit, a very positive benefit. It actually increased the rate of degradation in the plume. And that's not uncommon. We've seen that a lot of sites that are mature, been pumping for a long, long time, turning them off actually, lets the system go back to a more anaerobic condition and is more effective at lower concentrations at decreasing these plumes. And we've seen this time and time again. So here's the 2,4,5-T plume data. Again, post-shutdown data, very strong decreasing trend in the entire plume. So just again, this was a successful closure, turned the system off at that site. Very strong benefit, from a sustainability standpoint. So that's the first example I wanted to show you, and I'll show you a couple more here, examples of how these tools can be used at a site. So the second one is a bulk terminal. And this is a site that Kyle Waldron and Scott Stromberg presented, I think last August, on one of these webinars for SURF. So this is a little more detail of one of the sites they used in transitioning from an active to a passive remedy. But I'm going to dive into one of the plumes that we looked at. So for this site, it's a benzene plume. And again, I've already explained how Ricker method works. So I'll just start playing this. And the different colored wells are because there are three different entities of data. So you have a terminal here, another terminal here, and then I think a retail site over here. So they're just kind of a big shared data set. And you can see how the plume is behaving. A lot of the gray wells you see coming in over time, these gray wells are all different types of remediation wells that come in over time. And you can see how this plume is behaving. So again, all the way through January 2019, very strong. The colors got lighter. You could really see that in the data. I missed the trends on that one. So after we look at the plume decrease on that plume, we can look at the centers of mass, and you can see the center of mass. Again, the migration of the center of mass, you can see it really to the east. The darker colors shifting to the lighter colors. Now at this site, the groundwater flow is to the west. The bulk groundwater flow is to the west. But you can see, again, a very strong up gradient shifting in the center of mass data. And so I can, I didn't explain this earlier, but what this is over here is it's a way to look at individual movements of the center of mass. So if you've got a center of mass at one location and it migrates to a new location, just connect those 2 points with an arrow. mathematically that's a vector, and we can look at the vector movements over time. And so when I just zoom in on that, this is what I call a shotgun pattern. So the vector movements is just really all over the place, which is a really strong sign of stability. So the individual movements are very random in nature, but the bulk movement is really in the upgradient direction. So again, a very strong, stable signature in the center of mass for that particular plume. So now we'll look at again, the spatial change indicator for this particular site. And again, we're going to see a lot of the areas of blue that indicates attenuation. We have a few areas of the pink or the red that shows, concentrations have increased relative to the rest of the plume. You can see a lot of these darker areas where the remediation wells were pretty dark in the core of the plume. Again, the very dark blue on the outside indicating a 100% attenuation outside on the periphery of the plume. Very strong attenuation signature here. Again, you can look at the bottom, 94% decrease in mass, but only a 41% decrease in area. That's a pretty strong phenomenon I've noticed on a lot of plume data. You'll see the areal extent will decrease to some level, but what goes on inside the plume is generally a lot different than what happens at the periphery. So you can't always use the peripheral extent of a plume to describe the overall plume behavior. Again, at this site, you can see a very strong reduction throughout the plume data. One thing the Ricker method analysis tools let you do, it lets you do a little more detailed analysis. So what we can do here is what I've done is I've outlined 4 different remediation areas for this site. So there are 4 different remediation areas within these polygons. What we can do is focus in those polygons, do our spatial integration just inside those polygons and get a sense of plume behavior anywhere we want to see it. So if I start playing this video again, notice in this polygon, there's nothing there. Well, if I click on it, it takes me to the trends, the behavior for that particular area of the site. And you can see in the early data, there are no wells, so there's really no mass in there. You'll notice there's a network expansion here. So all of a sudden there's mass inside that polygon. It's not because it grew or because the plume's moving there. It's just because wells were added and they found more data, more information. You can see a second expansion changed the way it looked again. And then from that second expansion forward, we can track the progress of behavior just inside that polygon. So when I come back to it, we'll let the video restart. You see these wells come in, that's that first network expansion. Boom, a second well comes in way up here, that's a second expansion. So you can see it in the data, what's going on, and we can just let this play over time. Again, you can see different times when these remediation wells come in. Some are SVE, some are dual phase extraction, O2 injection, just a lot of different types of systems installed across this project area. So now it makes a little more sense when I come back to this window and I click on it, I can look at the behavior. You see when that dual phase extraction, those wells were installed about 2011 timeframe. Kind of zoom in on this, you can see, pretty strong behavior, and then really strong after that system was shut down. The plume did not rebound, stayed at a low concentration. Again, helping to keep that system turned off. Help to evaluate the turn off, shutdown, and remaining shutdown of that dual phase extraction system. So again, this was a really useful way to evaluate termination of remediation systems at that site. So just if you're curious, we can look at these other areas. Look at this area up here that had SVE and O2 injection. Different part of the site, different behavior. It's one thing that's really important to stress, especially large plumes. Different parts of the plume behave differently. So when you do want to focus in one part of the plume, this is a helpful way to do it, looking at polygons in specific areas of the plume. So again, you can see when the SVE started, O2 injection, again, the plume behavior in those areas. We can look at the middle area. Again, different behavior, different remediation periods, different remediation techniques, but you can see how the plume was behaving for the plume mass and average concentration as well. Then I'll just hit that last one just for see how, just a little more variable. The important thing is when those systems were turned off, we did not see an increase or, an expanding plume, things like that. So again, another strong way to use the Ricker method to evaluate termination of remediation systems. So at this site, we also used that well sufficiency analysis to evaluate network reduction. So that's the next thing I'll show you using the same site. doing a well sufficiency analysis. So I'm not going to play this whole video again, but this is the exact same benzene in the A zone video I've already showed you. Here's the total trend data, area concentration mass for that site. We're going to focus in on just the last 6 years and look at the behavior just during that period. So I'm kind of zoomed in now on the area concentration and mass for that plume in just the last 6 years of operation for the site, okay? And again, nothing new here, but we're gonna make some comparisons. So the first thing we'll do as part of the well sufficiency is we're going to use a quasi-professional judgment approach and just simply remove wells from the analysis. These wells that are in purple, you see all these in here, we indicate that we're going to take that out of the analysis, rerun it, and see if we get similar behavior or metrics in the plume. And this is an iterative approach to evaluate, if a well is useful or not. So I come back to this chart, I'm looking at the plume behavior with all wells in the network. And now you see the orange line is what the trends would be with those 7 wells removed. It's about a 10% reduction in the area. We look at the trend data. We want the trends to match. We also look at average relative percent difference of every point on the line. And then we also look at the correlation. They should behave the same. Well, this isn't awful. This isn't a bad analysis. It looks pretty good, actually, because our interpretation would be the same. My conclusions would be the same. Our understanding of behavior would be the same with 7 fewer wells. Well, what we do is we go back and take more out. So now 14 wells removed. All these wells in purple have been removed from the analysis. And so we continue this again with 14 wells removed and do the same thing. Here's what it was. This actually got better, and I've seen that. It actually gets better sometimes with removing certain wells in certain locations. So a 21% reduction, again, same conclusion, same interpretation. We keep going. So this happened several times, and we ended with 27 wells removed. So you see all the wells in purple have been removed, 27 wells removed, and you really can't see it in the video how the plume is behaving, but that's why it's always nice to look at it objectively in the trends. Here are the trends at the end. So at the end of the day, we had 27 of 68 wells removed. That represents about a 40% reduction. In all, actually, there were 34, I think, of 92 wells, because there's the B zone also. We did this for 2 zones. We did it for benzene, for TPH, TENX also. So every compound that you're looking at, we do this for. I'm just showing you individual compounds for just as an example. So at this site, a 40% reduction in your well network is from a sustainability standpoint is fantastic. That's 40% fewer trips you got to make, 40% reduced cost, analytical cost. So many benefits using existing data. That's the great thing also. This is an empirical analysis. There's no calibration. We just take existing data to do these types of analyses. So just coming back to this, there's the current network, there's the proposed network. You can see it still has plenty of coverage, and it was actually a really good way to not only get help evaluate termination of systems, but also to reduce the network and frequency of sampling. So just a really strong way to evaluate sustainability for that particular site. So the last one I'm going to look at is Chem-Dyne. And this is interesting. This is a chlorinated site. A lot of you guys probably have chlorinated sites. This is a very large, this is actually one of the first NPL sites. So this is one of the original sites on the NPL back in 1982. I think it was 143 original sites back with Love Canal and all those guys on the original site of contaminated sites on the NPL. This is one of them, Chem-Dyne in Hamilton, Ohio. Very contaminated site. We have total VOCs in excess of 50,000 parts per billion throughout the plume. And this is just chloroethenes. I'm just showing you chloroethenes. I got to simplify it somewhat to show it to you. These red wells are extraction wells, and you can see the total extent of the plume. This is what the plume was in 2014 when we turned the system off. And I'm actually not going to focus on turning the system off. What I'm going to focus on here is how we evaluated the post-shutdown data to demonstrate unequivocally that natural attenuation, i.e. biodegradation, was continuing, even when EPA said it wasn't. And I'm going to show you a really cool way to evaluate that. So that's just the data. Here are the trends. Typical pump and treat system, very high concentration, rapid reduction, asymptotic for many, 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 many years. We finally turned it off in 2015. And so what I'm going to do is I'm going to focus on, again, the data post shutdown. To do that, I'm going to go back a little bit, but just to 2010. And I'm going to start with tetrachloroethene. We're going to look at chloroethenes only. So what you're looking at now is the PCE plume, and it's going through time here, just going, just typical what I've already shown you how these work, area concentration mass. You can see the tetrachloroethene plume through June 2020, and then looking at the trends in the data for tetrachloroethene, you can see it prior to shutdown. Here's when pumping was terminated, and then here we have the post-shutdown data, very strong reduction in PCE, and so that's really, really good. And I'm going to paint this story much better here shortly, but we'll look at TCE. I just wanted to show you the process. So we do individual analyses for each of the constituents of concern when you have a chlorinated family of compounds. So this would work for chloroethanes, chlorobenzenes, chloromethanes, whatever your family of compounds is, you need to look at the individual compounds first, and then we'll look at them on a total chloroethene basis. So here's TCE, again, the TCE data decreasing over time. That looks really good in the post-shutdown data. So now we look at cis-1,2 DCE. This is where it's going to get tricky. So here's the cis-DCE data. We're actually looking at it down to 5 parts per billion so we can evaluate behavior. We really want to look at that degradation behavior, the breakdown of PCE to TCE to cis-1,2 DCE, which breaks down to vinyl chloride. Really want to focus in on that. So again, here's DCE to the end, and you see it is actually slightly decreasing over time. And then I'm going to show you vinyl chloride. And we're going to tie it all together here shortly, but I just wanted to show you all the individual analyses that go into a total analysis. So again, remember 2015 is when the system was shut down. I forgot to mention that. The system was shut down in 2015, and then we've got 5 years roughly of post-shutdown data. And again, very decreasing trend in the vinyl chloride data. So now we get to the total chloroethene plume. And so to do this, you'll notice we've switched over from weight concentration basis to a molar concentration. So notice our concentrations are now nanomoles per liter. Now, before I do this, I always like to do this, before I show this to you guys, show a little primer on why it's important, very, very important when you do chlorinated site data with families of degrading compounds to convert everything to a molar basis. I know a lot of you folks do this and it's routine, but I see it a lot in our industry where people do not do this and it can hurt you in some ways, and I'll highlight that in a moment. But so just a real quick, I'm gonna drop into this primer. So just hang with me if you guys are already doing this. When you look at this data set, I always like to ask people, I know you can't answer me now, but I always like to ask it if I'm in a group setting, is this a good trend or not? And what I've got is PCE, TCE, cis-DCE, and vinyl chloride, and then a total VOCs. Notice it's micrograms per liter, weight concentration basis. Is that a good trend or not when you look at that? And it's just adding them up. That looks good, right? You think, well, yeah, that's a decreasing trend. Well, in fact, here's the exact same data on a molar basis. Not only is it not decreasing, it's increased. And I'll explain why that happens. So here's typical data, how they're presented. So on the top, theoretical breakdown of PCE is the dark red. When it breaks down, it creates TCE. When it breaks down, it makes cis-1,2 DCE. It breaks down to vinyl chloride. You can see when you add them up, as it decreases, the total VOCs decreases right away. On a molar basis, nothing happens. And that's simply because 1 molecule of PCE makes 1 molecule of TCE. You're not destroying it, you're just converting it. And that happens until you get past vinyl chloride, until you've actually fully mineralized that compound. It's no longer a chlorinated VOC, it's actually just CO2, water, and chloride ion. It's just benign end products. But until that point, it's just converting along a series. And so a total VOCs on a molar basis, you really can't take credit for attenuation, or you really can't say you've got degradation or any type of attenuation until you see a decrease on a molar basis. And so to help explain that, again, that just shows you see there's some decrease here. Really nothing happens yet here. So to help explain that, you guys have all seen this breakdown sequence. PCE breaks down to vinyl chloride. You can just see that's a pretty common diagram, what I like to do is make it something that I can understand. It's easy to see. I use this in courtroom settings actually for litigation, and even attorneys can understand this. So not a big on attorneys, but this is a great way to help visualize it for stakeholders and other lay folks. Visualize it like hamburgers, with PCE being a 4-patty hamburger. Each patty represents a chlorine. A TCE is 3-patty hamburger, a DCE is a 2-patty, and vinyl chloride is a 1/4 pounder. And you think about it, if I've got a tray of 10 what I call Sasquatch burgers, I got a tray of 10, 1/4 pounders on the other hand, one's gonna weigh a whole lot more. I've got 10 pounds over here, but this is only 2.5 pounds, but the number of burgers is the same. It's the exact same thing with plume data. If I have some mass of tetrachloroethylene, say 10 molecules or 10 million or 10 billion molecules, and it all breaks down to vinyl chloride, it's going to weigh a whole lot less because there's fewer chlorines attached to it. So if I've got 10 milligrams per liter of PCE and it all breaks down to vinyl chloride, my total VOCs all of a sudden goes to 3.8. Well, I can't really take credit for degradation here, or for a complete attenuation or mineralization. I've just converted a lot of bad stuff, to a lot of really bad stuff. Is really all that happens in that case. So here's some examples of how this happens. Let's say I've got a site with, I'll represent it by 400 PCE burgers. It's all PCE. And over time it breaks down. Some stays as PCE, 25% breaks down as TCE, 25 breaks down as DCE, 25% breaks down as vinyl chloride. And in the end, my total concentration is less, but the molar concentration is the same. It's like being at this part on the chart. I think I've got decay, but I really don't. I've just got conversion. So this is where you want to be to show when you have attenuation, looking at your mass concentration or weight concentration gets lower, and now your total molar concentration gets lower also. This is where you can really start taking credit for attenuation, biodegradation, when your molar trend is decreasing within your plume. So here's the issue. Go back to the exact same example. Let's say I've got commingling. Second plume comes in. It's made up of TCE, DC, and vinyl chloride. Well, if I look at the total data, look at my mass concentration, it's still less, but my molar concentration went up. This actually is based on a real case I had where we had some migration of a plume. They were saying it was from degradation, and on a molar basis, that would be impossible. Actually, this is what happens. You're coming along, got some nice decay going on, and then boom, second source comes in. Well, on a total VOC basis, that looks like a decreasing trend. On a molar basis, it's actually increasing. So you got to be real careful looking at total VOCs, what units you're using. Just a real quick primer on why we do that, why it's important to look at data on a molar basis. So here's the total molar data for the Chem-Dyne site. And again, from 2010 going forward, I'll just make this go a little faster. We'll get to the end of this, total chloroethenes prior to shutdown. After shutdown, I have a decreasing trend in the total molar plume. Boom, that's fantastic. I can say absolutely unequivocally, post shutdown, my molar plume is decreasing. It's not going deeper, it's actually degrading. So this is a really strong way to show that. However, looking at some individual trends, I'll do this real quick here. Look at the highest concentration well, MW15. Here's again, you see the total molar trend going down. So the yellow is the total VOCs, the individual makeup now on a plume-wide basis. This is based on Ricker method analysis. This is a well by well, I'm sorry, this is the well data. The individual makeup within MW15. You see PC in red, TC, DC, and vinyl chloride. Well, look at the DCE trend. It's slightly going up over time. But look at the PCE, it's actually going down. So where's all that PCE going? It's not creating much DCE here. So look at these other wells. Look at SE6. I'm gonna zoom in on that. Look at the Cis12 DCE, no doubt. Look what it was before, after shutdown, it's taken off, just a really, DC is going up, all right? And you can see that DCE is increasing in that well. Look at SE3, which is down gradient. Groundwater flow here is to the top of the page. The coordinates are twisted here, but the flow is actually to the northwest, to the top of the page. Zoom in on that well, and again, look at the Cis DCE, really taking off. Lots of DCE being generated in a shutdown mode. Come over here to MW31. Zoom in on the data, same thing. Sys12 DCE is really taking off. Come into SE7 over here, zoom in on it. You know, the DCE data is pretty stable. So what happened here, when we were making this argument back in 2018, US EPA said, M&A is not going to work here. You cannot use that. You have to go back to some engineered remedy. And their only reason was because you have DCE stall. You know, so that's the question. You know, DCE stall is absolutely happening at this site. And so for that reason, M&A is not a sufficient remedy to carry this site going forward. Even though you shut the system down, because of the stall, you know, it won't work. And however, EPA was actually pretty wrong on this. It was not stalled at DCE, even though you saw a lot of DCE increases. And I'm going to show you why. So let me take you back. We're going to focus on this data set right here. Here's the plume data for the chloroethenes from shutdown to 2018. This is when EPA made their argument that M&A is not going to work because of stall. So this is the data set we had to work with right here. So when I zoom in on this, we're going to walk through this, why I'm going to show you that it was not stall. And to do that, I want to walk through another primer. And I know you guys, I don't know, I hope you guys don't mind this. I like to show examples that make things easier to see. So if especially this will appeal to any engineers or chemical engineers out there, the first day of class, you'll learn these equations. You know, go to any chemical engineering textbook, you'll find these equations. Very simple. For any system, input minus output equals accumulation. Real simple formula. If I rearrange that formula to solve for output, it's input minus accumulation. This is easy stuff here, guys. Another equation we can use, very elementary equation, accumulation can also be solved by taking the final value of a system, subtracting the start value of the system, and that equals your accumulation. Very easy formulas here. So if I have a tank, let's say it has 2 gallons, 2 liters of a fluid in it, that's the start value. Let's say I add 10 gallons to it. So this is easy, follow me here, and I now have 12, okay? Real simple here. So my final value is 5. How can I solve for my output? What was the output of the system? Now we know intuitively, I had 12, I end with 5, it's got to be 7, right? 12 minus 5 is 7, that's easy. But let's do it using our equations. Come in here, accumulation equals final value minus start value. Remember, my final value was 5, my starting value was 2, so my accumulation is 3. I'm gonna use my second equation now, output equals input minus accumulation. My output is my input, which was 10 minus my accumulation of 3, so output equals 7. Hopefully that makes sense because we're going to apply this to a system of tanks or a system that is now comprised of degrading plumes or degrading chemicals. TCE, when it breaks down, we're going to assume it all breaks down to TCE. It loses a chlorine, it degrades to trichloroethylene. It's going to break down and drop into the DCE box, and it's going to create DCE. When DCE degrades, it creates vinyl chloride and so on. And so we're going to apply this to a system of tanks here. I'll wrap this up here real shortly. If I've got PCE, I can measure the plume data. I've already showed you Ricker method analysis. I get the mass of the plume. I have the final value. You know, this could be moles, 10 moles of a plume, the start value of 20. My input is 0, which is conservative. I won't go into the reason why, but it's conservative. My accumulation is final minus start, 10 minus 20. I have a negative 10 accumulation here. So instead of output, I'm going to use the term decay because decay means something in our industry much more than output does. So we're going to say decay when something decays to another species. So decay now, my output of the PCE box is input minus accumulation. My input was 0, my accumulation was negative 10. 0 minus negative 10 is 10, so net decay is 10. So I'm creating 10 moles of TCE. Do the same thing. My input was 10. Take these measured values from well data. I can create plume maps and generate these plume masses here. 24 minus 32, accumulation negative 8. My decay is 10 minus negative 8, or 8. I have 18. So I'm creating 18 moles of DCE. Now look at the data here. When I'm doing my plume data, my start value was 40, my final value was 50. this plume is increasing, it's accumulating. So accumulation is in fact positive. 50 minus 40 is 10. So this plume is increasing, it's growing. Cis DCE is growing at 10 moles, let's say over a year's period, 10 moles per year. What we so often don't realize or we neglect is that 18 moles per year are being generated. So I have 18 being generated, I'm accumulating 10, so I still have a net decay of 8. Even though the plume is accumulating, it is still decaying. The net decay of 8 to vinyl chloride, same thing. That plume is also growing, and you can see the net decay here of 7. So the net out of that is 7. Coming back to Chem-Dyne, we're going to do the exact same thing. So this is the total plume mass. It's in moles, total plume mass in the gold. I've got the individual plume makeup in there. So the dark red is PCE. I can look at the regression of that line. What is the slope of that line? What is the accumulation? Remember, accumulation is the final minus the start. I can get that. The slope of any line is simply a rate. That's our accumulation. So my accumulation rate of PCE is minus 4.63 moles per year. I'm going to drop it into this table down here that helps me keep track of this. So if my input was 0, 0 minus a negative 4.63, I have a net decay of 4.63 moles per year. So remember, I'm generating 4.6 moles per year of TCE. Look at the TCE in place rate. Minus 2.81 moles per year is the accumulation. Now the net decay is now the input, which is 4.63 minus a negative 2.81. So I have a net decay of 7.8. So stop right here. At Chem-Dyne, we are generating 7.8 moles per year. That's how much is creating DCE. So look at the DCE rate. Remember, so those trends that were going up and those well by well charts, some are stable, some decreasing, some going up. On a plume-wide mass-based basis, the net DCE plume was in fact increasing 0.7 moles per year. So that's my accumulation. My DCE plume was actually accumulating at 0.7 moles per year, but my net decay, 7.8 was being generated. Net decay was actually 6.7 moles per year. So that plume was not stalled, it was decaying quite readily, even though it was accumulating. Look at this, the vinyl chloride data. It was also growing at 0.75 moles per year, 6.73 minus 0.75. I have a net decay of about 6 moles per year. And mass balance, that matches the attenuation rate. By the way, all of these are attenuation rates. So anybody looking at attenuation rate analysis, that's what these are. Ricker method is a great way to evaluate attenuation rates of individual species that make up an entire plume. So actually, we have a net decay of 6 moles per year. So the very important point here is accumulation does not necessarily mean stall. We showed this to EPA, walked them through it, and by gosh, they actually signed the approval. We have M&A as a final remedy, at the site, thinking it was stalled at DCE when in fact it was a very strong attenuation. It was decaying quite readily, but you got to generate those daughters to get to the end, even though it was decaying much faster than it was accumulating. So very strong analysis. Just real quick, some ancillary data here. Here's that same chart. Look at the molar fractions of the entire plume data. So the total molar mass of the plume is going down. Look at the molar fraction or molar ratio. PCE molar fraction is going down. The fraction of TCE throughout the plume is going down. The fraction of cis DCE is going up. The fraction of vinyl chloride is going up. This, my friends, is a textbook picture of reductive dechlorination. This is what you want to see if you want to demonstrate reductive dechlorination. So again, just a lot of data to help show that once you turn a system off, we got to be able to show that it continues, and effectively communicating it. I'm going to go back to the webinar that Kyle and Scott did, and I wrote this down, Scott. This is one of the key points. One of the key points from their presentation was effective communication with the regulatory agency. This is key. When you can use these tools to effectively communicate what's going on at your site, really helps get to that part of your analysis where you want to demonstrate closure. By the way, this entire example is highlighted in a published paper as well. This molarity provides better clarity, and it just speaks to using molar-based data. This is published in Environmental Forensics last year. This is also freely available. If you guys need or want any of these published papers, please reach out, email me, call me, I can get those to you. So those are just 3 examples. There's so many more I wish we had time for, but I'm going to pause and turn it back over for questions. Thank you.
Great, thanks, Joe. As always, a great presentation. We have a few questions coming in, so I'll go ahead and give a quick note too. Just a reminder that we do have a handout, PDF handout of this presentation on the handouts here, as well as this recording will be uploaded to the SURF YouTube channel here in the next few days as well. Yeah, but getting going, Joe, what are some of kind of the data requirements that you guys need to do this analysis? How many years, how many wells, that kind of thing?
Okay, so yeah, that's a good question. Typically, it's well data. The really what we need, what we would do if you were to do this analysis, again, it's a plume-based approach. So, your database of analytical data, generally, a lot of states, especially, they require, a sufficient number of data points. A lot of times that might be 8, but you got to be careful. 8 semi-annual events may not be sufficient to really get a good picture, or 8 quarterly events, 8 events over 2 years. It's not a real long window. I would rather have 8 years of data rather, so it's really depends on your site, depends on your network. But the way I like to think of it is if there's enough data or sufficient wells to create a plume map, then you generally have enough data to create, or to do this type of analysis. If you have a sufficient network. So, there's not a cut and dry answer to that question, but certainly if you've got a mature plume, you more than likely have the data needed. If you're generating plume maps, there's likely data sufficient to do this type of analysis. Hope that answers it.
Yeah, I think that's great. Yeah. How long does it typically take you guys to do an analysis like this for a site?
So of the 3 examples I showed, they're typically 4 to 6 weeks, I think is the typical time frame. Now we do this for small, smaller retail type sites. It might be a few weeks. The larger, we do work for like some of the DOE sites they have, my goodness, 4-mile long plumes, several hundred wells. Those might take a few months, but I would say most cases within 4 weeks we're going to have all the plume maps, all of the analyses, kind of a draft look at it, but generally 4 to 6 weeks start to finish is what this type of analysis would take for most sites.
Yeah. The question, in the case of the well network reduction example that was used, was any specific criteria or used to select the wells to be eliminated? If so, can you expand on how to choose those?
Yes, we can. So if you're going to do a well reduction analysis, the first thing, you can always cherry pick non-detect wells. Oh, but that's I just want to make a point. That's not always a smart move. Sometimes those non-detect points are very important in bounding your plume. So things like that. So if there's a well that's near a sensitive receptor, certain non-detect wells, we tend to say, well, that can't be used for reduction because it would really change the way the plume looked if we did it. So that and again, like I said, it's quasi-professional judgment approach. A lot of times use professional judgment, you just do it, go to the regulator and hope it flies. What we're doing is using professional judgment, and then you doing a scientific analysis that's empirically based and seeing if we can still understand the plume with a different network. So I'm not evading the question, but hopefully that answers it. It's really what you decide. What's a key well that cannot be removed? And again, it might be a permit required well. It could be a sensitive receptor well. But one thing I'll also say, a lot of times, well, people will say, you could just stop sampling all your non-detect wells. If you do that, your plume just expands. You don't have any bounding. So what I would recommend in those cases is those are prime wells for reduction in frequency. So say you've got a non-detect well that bounds your plume, well, sample that well at least every 5 years to verify that assumption still holds. Don't get rid of it, don't abandon it, maintain it, and sample it every 2, 3, 4 years to make sure that assumption that you're using is still valid. Hopefully that helps.
Yeah, I guess a kind of a follow-up to that is, with the wells that you pull out, do you see, I mean, you kind of touched on this already with the non-detect wells, but do you see certain pockets of plumes, like source area wells, having a bigger impact when you remove them versus just like the non-detect wells? Like any trends, I guess, in helping guide selection of what to pull, or kind of pull them and run the analysis and say, oh, that's a bad one to pull.
Well, and actually, Chris, you can recall this. This can be done quite readily.
Yep.
So, you can run through the iterations pretty quickly. So, literally 5 minutes. If you take out 13 out of 70 wells, like I said, literally within 5 minutes, we can see what the results are. You just rerun it. And so it's a very quick iterative process. So that, at least the tools we have developed so far, and again, these are not, I'll say just real quick, this is not software that we offer out yet. It's something we're going to work towards, but it's proprietary stuff that we've developed right now. But we can do it pretty quickly. So that doesn't really come up. We can run, dozens and dozens of scenarios in a day. So that really doesn't come up, but it can help. Yeah. Anyway.
Okay. Yeah. I guess kind of a relation to all of that is kind of a general idea of cost for using this at a site.
Sure. So cost. I like to say the median cost. Probably. I gotta go back. I gotta remember which site I was looking at. So each of these sites, and you guys got a sense of what the size and magnitude. There were multiple compounds. You can see we did BTEX, TPH, and all these. This one we did chloroethanes, chloromethanes, and chloroethenes. The median of these types of sites is in the neighborhood of $30,000 to $40,000. 30-40K is probably a median number. Like I said, the DOE 4-mile long plume sites with 400 wells, those are closer to 100K. The retail sites that are, a dozen wells, 4 years of data, they're more on the, 10 to 12K. But I would say the median is 30 to 40K to do this type of analysis.
Okay, and I guess one final question before we get ready to wrap up here is, if you've been able to use this to evaluate any PFAS plumes yet.
No, but we would very much like to. Yeah, as you all know, we're all still kind of swimming in this new world of PFAS. But personally, I don't have, or at least in my close network of clients, we've not done this, or I haven't done it on a PFAS plume, but I think it has a fantastic applicability to that. We did some really cool stuff with 1,4-dioxane plumes and even MTBE plumes, some of the other emerging compounds, but we just have not done it for PFAS yet. But not to say it isn't very applicable to it.
Okay, yeah. Well, I guess with that, I'll kind of bring Kyle back in to give a quick final closing here.
All right. Thank you.
Yeah, thank you everybody for your time today, and thank you, Joe, for taking the time to put this together and put it on for us. Really great talk. So just quickly again, find us on our website. You can find past webinars on our YouTube channel. This one will also be posted to it shortly. We'll have future webinars upcoming, probably the next one in second quarter sometime. Also, we're paired with AEHS West, the conference coming up next month. So we'll host some sessions there, some surf sessions. Surf will host a virtual happy hour and an open meeting that's you can attend if you're a member or non-member. And then finally, the last slide, Joe, just want to say a big thank you to our sponsors. They enable us to continue to do things like this. So Thank you very much. And a special thank you to TriHydro for always helping set these GoToWebinars up and hosting them on their platform. So with that, we look forward to having you all back at the next one at AHS. Thank you.
Thank you, everybody. All right. Bye.